Namaste everyone. Welcome to second PUC physics class. We were discussing about electromagnetic induction, correct? Namaste. Welcome to the class. We were discussing about electromagnetic induction which needs a change in flux. A change in flux linked with a coil always induces an EMF in the coil. That change in flux may be brought in many ways. I don't know how many, this is how many times I am repeating this sentence. So change in flux induces an EMF. So change in flux can be brought in many ways because flux linked with any coil is NAB cos theta, right? But theta is the angle between the normal to the coil and the magnetic field, right? Theta may be any angle, and the number of turns, area of the coil, strength of the magnetic field. Now, so whenever there is a change in the flux linked to the coil, it induces an EMF in the coil. Now we will look into that in different way. How to produce the magnetic field and make a change in the flux linked with the coil. You can do it in many ways. One way is coil and coil experiment. Another is coil and magnet experiment. So instead of a magnet, we are taking another coil, that's all. So here is a coil, and that coil is connected to galvanometer. So it has many turns and connected to the galvanometer in order to detect current, and here is another coil which carries current, and that current should keep on changing. Of course you can switch it on and switch it off, or you can connect an AC here. Now as soon as you switch it on, you know that the current starts rising, and that is called rising current. Make means switching on the circuit, and making the circuit increases the current up to a certain stage, and then it becomes steady. But during that there is an increase in the magnetic flux produced by this coil, and that magnetic flux is linked to the other coil. I will call this as secondary coil, this one, and this one as primary coil. So when there is a change in the flux, change in the magnetic field produced by the primary coil, and that induces an EMF in the secondary coil. Of course, secondary coil must be placed very close to the primary coil. So you switch it on and switch it off. As you switch it on and switch it off, the magnetic flux increases, decreases, and that induces an EMF in the secondary. And I call this process as mutual induction. Mutual induction. Yes. What do you mean by mutual induction? The change in the magnetic field produced by one coil induces an EMF in the other coil. That is called mutual induction. Now, so the amount of EMF induced here, so you will get an EMF here, and you will get an induced current also. And how much EMF is induced, the magnitude of induced EMF, that depends on how fast the magnetic field is changing, how strong the magnetic field will be produced by the primary coil, and how many number of turns are there in the primary and secondary coil, how much flux is linked, how close they are. If you keep this far away, flux linked with this coil may be very less. And number of turns in the primary, number of turns in the secondary, area of the two coils, orientation of the two coils. If the coils are not in a position such that the magnetic field of one coil enters the magnetic field of another coil, if it is turned like this, all the magnetic field lines will not enter the other coil if they are placed like this. And if they are placed like this, of course, no magnetic field will enter to this coil. It will just pass by the side of the coil. So it should be placed like this. So orientation, number of turns in both the coils, area of the coils, and the closeness they are, how close they are, and the core in between them. What do you mean by core inside the coil? Yeah, you know that if you fill this, the two coils, if you wind the two coils in a ferromagnetic core, you take an iron rod, wind the two coils over the iron rod at the two ends, then the flux will be more. So that also will change the induced EMF amount. And that property, because of which a coil can induce a magnetic field in itself, or in itself, by the change in the magnetic field in the other coil, secondary coil, a change in the magnetic field of a primary coil. Secondary coil can induce EMF in itself. That is called mutual induction. This is one process. You have one more thing, that is, you take a single coil, okay, and pass current through that coil. So this is the coil, and here is a battery and a key. Switch it on and switch it off. As you switch it on and switch it off, won't that coil produce a magnetic field by itself? And won't that magnetic field change within that coil itself? So when you switch it on and switch it off, there is a change in the magnetic field produced by the coil, and that induces an EMF in the same coil, and that is called self-induction. Right? So you will get an induced EMF here. Change in the magnetic field produced by a coil may induce an EMF in the neighboring coil. That is one thing. It may induce an EMF in itself. That is called self-induction. And change in the magnetic field produced by one coil inducing an EMF in the other coil is called mutual induction. The name itself suggests which is mutual and which is self. This is self-induction. Now, so the magnetic field of this coil may change, and that may induce an EMF in the coil itself, right? So that is called self-induction. Now, self-induction, how much EMF is induced in this coil? And that depends on how many number of turns are there in the coil, and how much area of the coil is exposed to its own magnetic field. What is the core inside? You can fill this with an iron core, right? Iron core. Induced EMF will be more. And what is the core? What is the number of turns? So everything, right? So the self-induction or induced EMF, self-induced EMF depends on the number of turns in the coil, area of the coil, and the core inside, everything. Core means on which it is wound. If it is wound on a ferromagnetic material, of course induced EMF will be definitely more. Okay, let it be. Now, how do you measure it now? See, there is a quantity which decides how much EMF is induced, and I call it as self-inductance here, self-inductance of the coil, and I call here it as a mutual inductance. You know that the induced EMF depends on the number of turns, area of the coil, orientation, core, everything. So everything together I call it as mutual inductance. I will define what is mutual inductance. Process is called mutual induction, and the ability of the coil to induce EMF because of the change in the magnetic field in the other coil, that is called mutual inductance. Ability of the coil to induce EMF in itself because of the change in the magnetic field in itself, that is called self-inductance. For example, when you connect a battery across a rod, iron rod or metal rod, what happens? Electrons will flow, but electrons can't flow easily. They experience a opposing force because they experience a collision, so they lose energy. So because of collision, that is called resistance. What is resistance? It is the property of a material which opposes the flow of current. On what factors resistance of a material depends? Resistance of a material depends on how many number of electrons are available per meter cube, free electrons, and what is the area of the material, and type of the material, that is number of free electrons available per meter cube, that is the type of the material, and area, length, and all, right? So material, type of material, area, length, temperature, all these decide resistance. Resistance may vary for different length. Similarly, the amount of induced EMF in the coil, when there is a change in the current through the coil itself, what you call self-induction process, and that EMF induced depends on the self-inductance of the material, ability of the material. And on what factors self-inductance depends? Self-inductance depends on the number of turns in the coil, and area of the coil, core inside the coil, length of the coil, it may be a solenoid type, so everything. Similarly, mutual inductance depends on number of turns in the coil, area of the coils, both the coils, orientation of the coils, core, so everything, right? So you should have a formula for mutual inductance and self-inductance. I will use a symbol, self-inductance, L, mutual inductance, M, right? Now, as if you have resistance, R. R depends on what factors? R depends on length, area, and material. Finally, you have a formula for resistance, R equal to rho L by A. How do they depend? Resistance is directly proportional to the resistivity of the material. It is directly proportional to the length of the material, inversely proportional to the area of the cross section of the material. So they decide what is the resistance. Similarly, self-inductance should depend on the number of turns in the coil, area of the coil, orientation, everything. So that you have to have a formula for self-inductance and mutual inductance in terms of number of turns, length of the coil, if it is a solenoid type of coil, and area of the coil. All these things must be shown. Core, what type of that coil is wound over what type of material, and that also should decide. Its permeability actually. You know that ferromagnetic material is a very good magnetic material because of its high permeability, right? Right. Now, so we should have a formula for this. Hope you have understood what we are going to discuss now. So the ability of the coil to induce EMF because of the change in the magnetic field in the other coils, primary coil, that is called mutual inductance. And ability of the coil to induce an EMF in itself because of the change in the magnetic field in itself is called self-inductance. Right. Now how to analyze it mathematically now? So you have to go scientifically, and this is a general definition, ability to induce EMF in itself and all. Okay. You have the formulas like this. Now you know that you start from this Faraday's law. Induced EMF magnitude is directly proportional to rate of change of magnetic flux, or is equal to rate of change of magnetic flux. So if I write magnitude wise, magnitude of induced EMF is equal to rate of change of magnetic flux, right? But you know that flux, how much flux is induced to this coil, how much flux is induced to the coil itself, self-induction. That depends on mainly the current, because once you select a coil, usually we don't change the number of turns, we don't change the area of the coil, that will be fixed. Once physically we select a coil, it will be fixed. We will change the current. That is the easiest idea to change the magnetic field, because flux is equal to NAB cos theta, but B is equal to mu naught Ni, correct? Mu naught Ni, where N is the where I is the current passing through the coil. It is a magnetic field produced by a solenoid, mu naught Ni, inside, right? Magnetic field inside a solenoid, mu naught Ni. N is the number of turns per unit length, small n. Capital N by L. Small n is always for per unit length, number of turns per unit length. Capital N is N by L. Capital N by L, length of the coil, is small n. Okay. So you can change current I. Now that means if you want to change the flux, when you switch it on and switch it off, switch it on and switch it off, current rises, current falls, or if you connect an AC, current changes by itself sinusoidally according to sine wave. Okay, if it is so, how much fast the flux changes depends on how much fast the magnetic field changes. In turn depends on how much fast the current changes. So shall I write it as di by dt? Okay, I can use capital I, di by dt. So rate of change of flux depends on rate of change of current, because flux is magnetic field per unit area. Okay, flux is the number of magnetic field lines per unit area. So once the magnetic field decides the flux, magnetic field is controlled by current. So rate of change of current is the rate of change of magnetic flux. d phi by dt is equal to a constant called m di by dt. Okay, I usually write in small letter, whatever it is, m di by dt. What is m? M is a constant called mutual inductance of the two coils. That is where it comes. You know, current is directly proportional to voltage, and V proportional to I. V is equal to I into R. That's what we write, correct? That is Ohm's law. R is a constant called resistance of that material. For this pair of coils, M is a constant. M is called mutual inductance of the pair of coils. And integrate this, what you will get? Phi is equal to, if you integrate this, phi is equal to Mi, isn't it? Phi is equal to Mi, and okay, so actually if there are n number of turns, you have to multiply it by n for n number of turns. N phi is equal to Mi, and actually it is suppose you pass current through the primary coil. If you are passing current through this coil, and that produces a change in the magnetic field and linked to the secondary coil. So this is the mutual inductance of the secondary coil with respect to primary coil, right? Mutual inductance of the secondary coil with respect to primary coil, and current through the primary coil. Then, so like this, we will discuss it later. So simply I will write N phi is equal to Mi. N phi is equal to Mi after integrating with respect to t, right? N is brought because it depends on the number of turns. That I haven't, okay, N d phi by dt, I can include this, because more the number of turns, more will be the flux linked with the coil. Okay, so N phi is equal to Mi, and okay, right, Now you have to define what is mutual inductance. Yes. Okay, here you have to come now. What is L then? Self-inductance. Same theory here. Induced EMF is equal to d phi by dt. Magnitude I am writing, but it is proportional to di by dt. So d phi by dt is equal to L di by dt, right? And phi is equal to Li. Very simple. Not for the sake of examination. So n you have to include. N. It is only for the sake of knowledge. So n phi is equal to Li. So where L is the self-inductance of the material. Okay. So now we will try to define what is this self-inductance and mutual inductance clearly in some terms, right? So we will take a coil and we will define what is self-inductance. Already we know that self-inductance and mutual inductance should depend on the number of turns in the coil, area of the coil, and all those things. But we will define it clearly. Now take a coil, right? I will go for self-inductance first. I'll start from here so that I will have enough space for mutual inductance also. Self-inductance, Induction is the process, self-inductance is the ability. So I will take a coil having many turns and I will connect it to a battery and I will vary the current when I switch it on and switch it off, or I can connect an AC as an AC source itself. Now when I switch it on and switch it off, you know that the flux through it changes. The magnitude of induced EMF E is equal to minus d phi by dt. Now I will take the negative sign also according to Lenz's law. But d phi by dt is directly proportional to di by dt, the rate of change of current, how fast the current increases and how fast the current decreases. Accordingly we have the magnetic field also. So now shall I write E is equal to minus d phi by dt, but that is equal to minus L di by dt. Again, negative sign is in accordance with the Lenz's law. I have not discussed this in the previous discussion, right? That minus sign. Of course you can, because we have taken only magnitude of induced EMF. So now, shall I write E is equal to minus L di by dt? This much. That's enough for me. Now I have to define, using this formula, what is self-inductance. Now what I can do is, I can do it like this. See, for example, this you will understand. You said, you know Ohm's law. Current through a conductor is directly proportional to the potential difference. And V is equal to IR. We have that. V is equal to IR. That is Ohm's law. What is R is equal to V by I? Suppose you want to find out the resistance of a material, you can do it like this. What you can do is connect a voltage across the, apply a voltage across the resistor or a metal. Apply a battery. Measure the potential difference. Let us assure that the current is 1 ampere. Select the battery which can pass 1 ampere and measure the voltage across the, that resistor. So take a resistor, connect a battery across this and make sure that this battery passes 1 ampere current only. Okay, it's not like this, current like this. So 1 ampere current only, I is equal to 1 ampere. That should be very sure. And when I is 1 ampere, what is R is equal to? V itself. Whatever voltage you get across the resistor, that numerical value will be equal to resistance. R cannot be equal to V. I am writing only numerical values are same. If we get voltage as say 3 volt, then resistor is 3 ohm. Only numerical value you can copy, not the unit. Unit cannot be copied because resistances and voltages are different quantities. So you can write it only when the numerical values are same. So how can you define resistance then? Resistance of a material is numerically equal to the voltage across the resistor when the current through the resistor is 1 ampere. When the current through the resistor is 1 ampere, whatever the voltage you get across the resistor, that numerical value is exactly equal to the numerical value of the resistor. So you can name it as, suppose you get 3 volt here, you can name it as 3 ohm. But resistance cannot be 3 volt. That's not possible. So you can define resistance, the resistance of a material is numerically equal to the voltage across the resistor when the current through the resistor is 1 ampere. So we will use the same procedure here. But this is not the best way of defining. Just for understanding purpose, this is good. This is not in the syllabus, but I will just discuss it just to make sure that you have understood what is self-inductance. Now, can I write, omitting this negative, can you write E is equal to L numerically? Yes, possible. When? when di by dt is unity, right? It is unity. So what is the self-inductance of a coil? Self-inductance of the coil is numerically equal to the EMF induced in the coil when the rate of change of current is unity. If in SI system you want to define when the rate of change of current is 1 ampere per second, then inductance is Henry. Of course, self-inductance unit is Henry. Unit is Henry, it is the name of the scientist, and H is the symbol. Since it is the name of the scientist, you are right. We are writing H, capital H as the symbol, and full name Henry, small letters. Okay. So define self-inductance of a coil is numerically equal to the EMF induced in the coil when current through the coil changes, a rate of change of current through the coil is unity. Now you said that SI unit of inductance is Henry. When will be the self-inductance of this coil? 1 Henry. We will define. What is 1 Henry? Okay, so take the same formula. Okay, we will write it as 1 Henry. So L is 1 Henry if what? E is 1 volt, because we have to select all SI system. Because Henry is the SI system unit. 1 volt, and di by dt is 1 ampere per second. This is what you have to select now. So define 1 Henry. Self-inductance of a coil is said to be 1 Henry if 1 volt of EMF is induced across the coil when current through it changes at a rate of 1 ampere per second. If current is increasing by 1 ampere every second, at the 0th second 0 ampere, first second, at the end of first second current rises and becomes 1 ampere, at the end of 2 seconds it reaches 2 ampere, at the end of 3 seconds at the end of 3 seconds it reaches to 3 ampere. So every 1 second, if it increases by 1 ampere, 1 ampere per second rate, or fall, even fall is good. So if the current decreases by 1 ampere per second or increases per 1 ampere per second, then whatever the voltage induced, if it is 1 volt, then self-inductance is 1 Henry. Self-inductance of a coil is said to be 1 Henry if 1 volt of EMF is induced in the coil, across the coil, when current through it changes at a rate of 1 ampere per second. That's one definition. So you have two definitions now. What is self-inductance? Numerically equal to the EMF induced in the coil. So how do we define it? Yeah, that is one part, right? So we define it here. EMF, self-inductance of a coil is numerically equal to the EMF induced in the coil. You should write numerically equal to. When the current through, rate of change of current through it is unity. If di by dt is 1, where is it? If di by dt is 1, then E is equal to L. And if you want to precisely define what is 1 Henry, L is 1 Henry if E is 1 volt, and this is 1. Everything is 1, then L is 1. So L is 1 Henry if E is equal to 1 volt and di by dt is 1 ampere per second. So self-inductance of a coil is 1 Henry if 1 volt of EMF is induced in the coil when the current through it changes at a rate of 1 ampere per second. Right, we will come to mutual inductance. You know that change in the flux of one coil, primary coil, changes an EMF in the, so this one like this, so here, it's not like this. Change in the current of the primary coil induces an EMF in the secondary coil, right? So this is the primary coil over which we change the current by switching on and switching off, or by connecting a AC source, whatever it is. And this is the secondary coil with galvanometer. Yes. Now, now there is a mutual inductance between a pair of coils. Now, how do you define this? E is directly proportional to d phi by dt, right? Or E is equal to minus d phi by dt. That is Faraday's law. E is equal to minus d phi by dt. But d phi by dt is directly proportional to di by dt. So E is equal to minus d phi by dt is equal to minus m di by dt. Right? E is equal to minus m di by dt. Now, Now you will take this one E as minus m di by dt. Minus sign is in accordance with the law of conservation of energy, that is Lenz's law. E is equal to minus m di by dt. Now define mutual inductance. Again the same method. Mutual inductance is always between a pair of coils. Now how do you define mutual inductance? Magnitude wise, E is equal to m if di by dt is unity. 1 ampere per second, 1 milliampere per 1 millisecond, whatever it is, whatever the unit you choose, it should be unity. Yes, define mutual inductance between a pair of coils. Mutual inductance between a pair of coils is numerically equal to the EMF induced in the secondary coil. You should be very particular here. EMF induced in the secondary coil, secondary, this is primary, okay. Mutual inductance between a pair of coils is the EMF induced in numerically equal to the EMF induced in the secondary coil when the rate of change of current in the primary coil is unity. Okay, that is, you should be very particular here. Mutual inductance between a pair of coils is the EMF induced in the secondary coil when the rate of change of current in the primary coil is unity. So very particular definition. Again, 1 Henry. What is 1 Henry? Mutual inductance is also measured in Henry. Whatever it is, inductance is Henry. What is 1 Henry? Okay. If, so you have the formula. E is equal to minus m di by dt. E is equal to 1 volt and di by dt itself is 1 ampere per second, all SI system, because we have chosen SI system 1 Henry. If di by dt is 1 ampere per second and dV by E equal to 1 volt, then m is also equal to 1 Henry. So define 1 Henry as the mutual inductance. For a coil, pair of coils, mutual inductance will be 1 Henry if 1 volt of EMF is induced in the secondary coil when the current in the primary coil changes at a rate of 1 ampere per second. Did you get it? So mutual inductance between a pair of coils is said to be 1 Henry if current changing at a rate of 1 ampere per second in the primary coil induces an EMF of 1 volt in the secondary coil. Very particular definition. So if an EMF of 1 volt is induced in the secondary coil when the current in the primary coil changes at a rate of 1 ampere per second, then the self-inductance is 1 Henry. Or if you want to generally define what is self-inductance, self-inductance is numerically equal to the mutual inductance. Mutual inductance is numerically equal to the EMF induced in the secondary coil when the current in the rate of change of current in the primary coil is unity. So all these definitions make us very clear what is mutual inductance and what is self-inductance. And later we should have a formula for mutual inductance and self-inductance. That is another part, right? Hope you will understand what are these definitions. Okay, so formulas: E is equal to minus L di by dt, very important, and E is equal to minus m di by dt. Mutual inductance between a pair of coils and self-inductance for a single coil. Okay, now we will try to have a formula for self-inductance and mutual inductance. First we will have mutual inductance. It looks horrible, that derivation looks very horrible, but it is very easy derivation. I will just start it now and then I will again do that in the next class also, so that you will get it back once again. Now if you want to have a best mutual inductance between a pair of coils, what you have to do is you have to put the two coils one over the other, wind a wire over a iron core and wind the secondary over that itself, so that no magnetic flux is leaked out, or it will not be linked, it will be lost without linking to the secondary coil. Let us avoid that such type of situation. So what I will do is, I want the color chalk today. I will take a coil like this. Say this is secondary coil. So wire is wound over this. Like this, and its two ends are here. That is S2. S1 I will keep it inside here. This is S1. Okay, primary coil. Okay, one coil is wound inside the other. Right, this one. So this is the one end and this is another end. Let both the coils have a length L. Right? N be the number of turns per unit length. N be the number of turns per unit length, that is total number of turns by the total length of the coil. That is N, right? So every term has to be very clear here. N, small n is the number of turns per unit length and capital N is the total number of turns. And I will show the axis. Let the axis be shown like this. Yes. This is a common axis for both the coils. So shall I name this as R1 and R2? Okay, this is R1 and this is R2. Radius of the other coil. Okay. Yeah. Now, which is primary and which is secondary? That selection is left to you. You can use you can interchange the primary and secondary coils. You will come to know, sir, if I change current passing through the secondary coil and find out what is EMF induced in the primary coil, if I do so, won't this self-inductance change? No. Self-inductance between a pair of coils. Sorry, won't the mutual inductance change? No. Mutual inductance is always between a pair of coils. Even if you pass current to the primary and find out the voltage at the secondary, or pass current to the secondary, find out the voltage at the secondary, one and the same. Okay, so how it is so? We will come to know that self-inductance mutual inductance between a pair of coils is always the same. Whether you take the primary or secondary, if you interchange it. So I will call this as coil 1, this as coil 1 because I have named it as R1, this as coil 2. Okay. Okay, now let us pass current through the secondary coil. So we will pass current through this one. Okay, and okay, here current through this one, that is I2, right? And let it come out here, I2, and find out how much flux is linked to the inside coil and what is the mutual inductance. That is our first aim. So you should be very cool and very comfortable while deriving this equation here for mutual inductance. So we will pass current through the secondary coil and find out what is the flux linked to the primary coil, and then find out mutual inductance of coil 1 with respect to coil 2, right? Mutual inductance of coil 1 with respect to 2. That is what we have to do. And you know supporting formulas. One is this one, number of turns per unit length. Then flux linked with the coils. Flux linked with any coil is number of turns, area of the coil, and magnetic field and cos theta. This is another supporting formula, second one. And third one, magnetic field due to a solenoid. That is the third formula, mu naught Ni. Mu naught N is number of turns per unit length. So any coil may produce magnetic field and it will feed it to the other coil, remember. So that is what is mutual inductance. Okay, right. Now we are finding out mutual inductance of the first coil with respect to the second coil. That means second coil is producing magnetic field and that is supplying it to the first coil. First coil is inducing EMF in itself. Okay, now you know this E is equal to minus d phi by dt, and that is equal to minus m di by dt, because d phi by dt is directly proportional to di by dt. So if you integrate this, what you will get? Phi is equal to mi. But if you want more number of turns, you have to include. This is another supporting formula. So n phi is equal to mi. N is the number of turns in the coil which is using flux. Remember, N is the number of turns in the coil which is using the flux, and phi, okay, of course, flux linked with the coil. M is the mutual inductance. I is the current through the coil which is producing magnetic field. So if you want to write this formula very particularly here, very carefully, number of turns in the coil which is used, which uses the flux, first coil, right? Number of turns in the first coil, and flux produced by the second coil, right? Or first flux used by the first coil itself. Okay, and then we will write this formula, phi is equal to NAB cos theta. Hope you are following, right? This is a very important derivation. N1 phi 1 is equal to mutual inductance of the first coil, because that is inducing EMF in itself. We are passing current to the second coil, and current is through the secondary coil. Second coil. I don't want to name it as primary and secondary. Actually now this becomes primary, one which varies current, and this becomes the secondary. But we will name them as coil 1 and 2. Coil 1 is enjoying the flux, and that is produced by the second coil. So current to the secondary coil. Mutual inductance of first coil with respect to the second coil, M12. And N1 phi 1 is equal to M12 I2. N1 is the number of turns in the first coil, because that is enjoying the flux, and flux through that coil. Now, if you want to expand it, now why can't I write N1 as in terms of number of turns per unit length? You see, what is the number of turns in the inside coil, first coil? It is N1 divided by L, its length becomes N1, isn't it? So what is N1, capital N1? That is small n1 into L. Am I right? Small n1 into L, because number of turns per unit length into the length gives the total number of turns. So this is what I have replaced for this one. Hope you have followed. Total number of turns in the inside coil divided by its length gives the number of turns per unit length in that coil. So N1L. Phi 1, what is phi? Phi is BA cos theta. Of course, N already have used. N already have used. Need not write once again. So N. Phi is equal to NAB cos theta. N already used. AB cos theta. Area of that coil which uses the flux. You see, flux is produced by the second coil 2 here. Coil 2 is producing magnetic field, but that magnetic field is used by the secondary coil. The coil 1. Coil 1 is using the magnetic field, flux, but its area is only this much. Sir, there is a magnetic field here, because you know that any solenoid will produce magnetic field like this, clockwise or anti-clockwise, depending on that current. It may be either like this or like this. So magnetic field like this. So there will be magnetic field lines inside a solenoid like this. Now the thing is, that magnetic field, suppose you place another small coil inside this, like this. What happens is, this coil uses the magnetic field lines only here, right? Only through this. If you have a large book, but you have only a small torch. If you have a large book and a small torch, see the difference. This is the torch. The light, luminous flux is only over this area. Am I right? Luminous flux is only over this area. You take the other way. We have a large torch, okay, producing large amount of light, whereas my book is only this much. Even though the luminous flux, light rays are passing like this, that is enjoyed by this book only this much area, correct? Hope you have understood. Flux is that magnetic lines of force or rays of light passing through the particular area. Here, even though the area is more, torch is only of this much, and only this much flux is passing. Now what is the condition here? Magnetic field is produced by the outside coil. It produces magnetic flux everywhere. There are magnetic field lines, there are magnetic field lines, there are magnetic field lines, but this is enjoying only this much, right? That's what I am trying to write here. Phi should be expanded, right? Or I will expand the phi first of all. AB cos theta. A is over already. N is already over. A, which area you will write? Area of the first coil. Why? Because that is enjoying the flux. There may be magnetic field lines here everywhere, but they are not linked to this inside coil. Inside coil, magnetic lines of force which are linked are only here, right? For the inside coil, magnetic lines of force which are linked only lie within this area. So you have to write the area of the inside coil. Okay, A1. B is produced by the second coil, magnetic field produced by the second coil. AB cos theta, cos 0. Did you understand? This has to be written as, so totally AB cos theta. Of course, NAB cos theta, area of the inside coil, because that is the only one which uses the flux here, and B2 because magnetic field is produced by the outside coil because we are passing current to the outside coil. Cos 0 here, why? When I place a small coil inside a bigger coil is producing magnetic field. Magnetic field lines are passing like this, and of course like this, here it is like this, and normal to the coil is also in the same direction, magnetic field is also in the same direction, cos 0, 1, right? Because in any solenoid, magnetic field lines are always normal to its cross-sectional area, and normal to the area itself, it lies on the same direction, so cos 0. So we have expanded N1, N1L, and A1, B1, 2 cos 0 is equal to mutual inductance of the first coil with respect to the second coil into I2. Now N1, L, A1, what is the area of the first coil? Pi R1 square, its radius is R1. B2, magnetic field produced by the second coil. Even though that is enjoyed by the first coil, second coil is producing magnetic field. Magnetic field is mu naught Ni, right? Mu naught, so I am expanding this now. Mu naught, what is the number of turns per unit length in the coil which produces the magnetic field? N2, I2, am I right? B2 is mu naught N2 I2, this one. Cos 0, 1 is equal to mutual inductance of first coil with respect to the second coil into I2, and cancel now I2, that is not needed. So what is the mutual inductance between a pair of coils? That implies M12 is equal to mu naught, I'll write mu naught first, N1 N2 mu naught N1 N2 pi R1 square L, pi R1 square L. This becomes the mutual inductance between the pair of coils when current flows to the second coil and first coil induces an EMF in itself, right? That is mu naught N1 N2 pi R1 square L. Now we will go other way. What is other way? It's raining heavily. We will go the other way. Pass current through the inside coil and obtain the EMF induced in the outside coil, that is second coil. So we will remove this. We will remove this. No current through the second coil now. Second coil is kept as it is. Let us pass current through the first coil itself, inside coil I1, and let it come as I1 outside. So current is passed through the inside coil, and it comes out through the it comes out through the other end, and it produces magnetic field, and that flux is linked to the second coil, right? Mutual inductance of secondary coil with respect to the first coil, that's what you have to write now, okay? Let me keep this and I will rub it later. Mutual inductance of secondary coil with respect to the first coil, what is this? Again the same formula, E is equal to minus d phi by dt is equal to minus m di by dt, and now n phi is equal to mi after integrating. Now we have to write this formula. What is this one? Number of turns of the coil which is enjoying the flux, that is outside, coil number 2. Coil 2 is enjoying the flux, and flux is enjoyed by the coil 2 itself, outside coil. N2 phi 2 is equal to mutual inductance of the secondary coil with respect to the first coil, second coil with respect to the first coil, and what is I? I is the one which passes through the now inside coil. We are passing current to the inside coil, I1. Hope you are following it. Passing current to the inside coil and finding out how much EMF is induced in the outside coil, that is 2, right? So N and phi, number of turns and the flux used by the that is outside coil, N2 phi 2, and M mutual inductance of the second coil with respect to the first coil, and I current through the inside coil, I1. Now you see here, and I will rub this and I will narrate it first and I will rub it. When you write phi 2, flux is used by the outside coil. Last time we were passing current through this and flux used by the inside coil. Inside coil was using the flux whose area is pi r1 square. Now which area will you substitute? You feel that you will substitute the area pi r2 square. No, it is not so. Why? Because when you pass, this logic you have to remember always. when you pass current through the outside coil was producing magnetic field everywhere, right? But that magnetic field was used by the inside coil only in this area. That's why we had pi R1 square. That is like passing light everywhere but having the book only this much, only area this much, right? Now the other way, passing current to the inner coil, it produces magnetic field only in this area, right? It produces magnetic field only in this area. Even though the area of the outside coil is more, even though the area of the book is more, we have the light only this much. So do you take if you want to calculate what is the luminous flux, will you take the full area? No, only this area, because light itself is falling on only this area. So even though the outside coil is larger in size, inside coil is producing magnetic field only in this area. So you have to put the area of pi R1 square only. You can't put pi R2 square because flux is only through this. Current is through the inner coil 1 and no current through the outer coil. So magnetic flux itself is available only this much. Light itself is available only in this area. You can't find out flux through the other side area here. Whereas here, flux is available everywhere, but area itself is smaller. This much is only enjoying the flux. So that magnetic lines of force passing through that much area, that you have to find out. So again pi R1 square only. That's why I have retained this diagram. Now we will write what is M21. Okay, so I will just, N2 phi 2. N2, number of turns in the coil 2. And shall I write it as N2L? This one, right? Or I will write it once again. That is better. N2 phi 2 is equal to M21 I1. Did you get that? Number of turns in the second coil, total number of turns. You know that total number of turns is number of turns per unit length into L. N2 into L. Then phi 2. Phi 2 is NAB cos theta. N is already written. AB cos theta. Area, that area through which the flux passes. You can't write pi R2 square. Hope you have followed it. Because over the full area we don't have flux because it is produced by the inner coil. Only through this area we have flux. Even though this has more flux, more area, it has no magnetic flux at all. So magnetic flux passes through only this much area. So shall I write this as area as pi R1 square, because I have to expand this area. B, magnetic field is produced by the second coil because it is, inside coil. Magnetic field is produced by the first coil. It is producing magnetic field. So B we have to write. B is mu naught Ni. Mu naught N1 I1 is equal to M21. Cos theta is cos 0, that you know. Magnetic flux is normal and normal to this area is like this. And M21 I1. I1 gets cancelled. What is M21? M21 is equal to mu naught N1 N2 pi R1 square L. Same formula, same as this one. So mutual inductance between a pair of coils, whether you pass current through the primary coil and measure the EMF in the secondary, or pass current through the secondary and measure the EMF in the primary, whatever it is, mutual inductance is same. M12 is equal to mu naught, product of number of turns per unit length, area of the smallest coil in them, and length of the coil. So that is how it depends. So mutual inductance depends on number of turns in the primary, number of turns in the secondary, their product. And whether it is N1, N2, N2, N1, no problem. Area of the smallest coil in them, length of the coils, and permeability of the medium. Suppose you fill it with a magnetic material, then mu you have to write. So a very important formula, and derivation also may be a little bit confusing. I have introduced something here. Neatly I will do it again in the next class, so that once you study it and come, whatever explanations I give, it enters your mind. Just look into that again and again. You will understand what are the things involved here. So try to get it back. Okay, in the next class I will do it again and we will go to self-inductance. Self-inductance is an easier derivation, and then we will move on. Thanks for watching my class. We will meet again in the next class with the mutual inductance and self-inductance. Thank you.